Hello YouTubers, and welcome to this session where we are going to have a little tutorial on how to use an oscilloscope. Now what I want to do, perhaps before we get into doing the tutorial on how to use the oscilloscope, is perhaps just explain a little bit about what it's used for and how it works. Now, so the one way I want to try and illustrate this is how it actually takes measurements and what a brilliant little device it is. If you can imagine this piece of paper, as you can see there's a little dot on the piece of paper. Now let's pretend that's a particular measurement value at a point in time. Okay. And we could pretend we're taking these even with a multimeter. And if we kind of flip up, we see, there we go, I've got another particular measurement being taken. There's another one being taken. Another one being taken. Yet another. And another. And another. And if we join all those measurements up, as an oscilloscope does, what you get is all those measurements being traced over time. And in essence, that's exactly how the old analog oscilloscopes work. They have a measurement which and they use those old CRT tubes, cathode ray tubes, and it would alter the beam, or the trace as it would call, as it got a signal. And because of your persistence of vision, your eye, it would actually draw a trace and join the dots or join the individual measurements across the screen. And that's in essence how the original oscilloscopes worked. Although it's obviously different today with digital ones, they just have the signal and they obviously plot it on a digital display. But in essence, what I like to think of an oscilloscope is a time machine. It really is a time machine. It allows you to see something over a period of time. Something that your normal multimeter can't do. In essence, your multimeter, if you can picture this as the screen, your multimeter allows you a little slither, a little slit window to look at a particular measurement, and if that measurement happens to be changing, you can only see an instantaneous value of that measurement changing. A multimeter is great if you've got a value which is reasonably constant and not changing much over time, because then you can see it instantaneously. But if you've got a measurement that's changing over time, i.e. an electronic signal, that doesn't help you. What you need to do is broaden the window so you see the whole picture over a period of time. And that's exactly what the oscilloscope does. It's a time machine for electronics specialists. Let's have a closer look. Okay, so we have our oscilloscope fired up and switched on, and we've got a signal that's coming through on it, and we've got all these knobs and buttons and what have you. So what on earth does all this mean? What are the bits on the display, and how do we use the buttons and the knobs to actually play with that signal so we can understand more about it? Well, let's have a look at some theory and a bit of a diagram, and then we'll get back to in practice actually turning the knobs on the oscilloscope to see how all that works. Right, so let's just cover off what on earth we see on the display and how that actual display works for us. Now don't be too worried about the kind of images and what I've got on this display. We'll cover that in a moment, but let's just first of all kind of look at the matrix of lines on the oscilloscope display. Now probably the first differentiating important thing, as I mentioned in this little time machine or oscilloscope, is the fact that you can represent time by the horizontal line, or the x-axis going along here. So on the oscilloscope, to make it easy to understand your time base or your time scale, they've broken it up into little segments, and these are this scale over here is obviously one of the things that you can adjust with the knobs or buttons on your oscilloscope. Now generally oscilloscopes, they can be broken, the size of the matrix can differ. I've got a matrix here of 10 by 10 in essence. There's divisions, and that's how they call them. So there's 10 divisions going up and there's 10 divisions going along the horizontal line here. Now that's known as your time base, and when you set your oscilloscope you can set what that time base should be, or it can be automatically selected for you, obviously, because you might not know the best time frame to view a signal. And as I've highlighted up here in the example I'm going to show you, each of those little squares is that division. And so, for instance, on your oscilloscope you may have it set to a setting of 500 microseconds, and that is a representation of each of those little segments. Now, if you happen to have it set at 500 microseconds, then in essence your full scale reading, and when I say full scale, your whole time base that you're showing in that screen would work out to be obviously 10 times that, which would be 5 milliseconds. So that's your horizontal or x-axis, and then we get to the vertical axis or the y-axis, which is an indication of the signal level, or for the most part on oscilloscopes, that is the voltage level of your signal. And again, it's divided up into individual little divisions, and each of those you can set with a knob to a particular value. And in the example that we're going to have a look at, each of those divisions is set to 1 volt per division, which means the whole screen shows a total value of, happens to be 10 times those divisions, which would be equal to 10 volts. So that's just something to understand, is that your y-axis or your vertical axis is the signal level in a voltage level, and your x-axis is your time. Okay, so let's quickly show you what that looks like on an actual oscilloscope itself with a signal. And again, before we get into that, what I want to show you is obviously the other important component of an oscilloscope is the actual probe. And I say, if there's enough interest in this video, and again, if you want to show interest in this video, then you need to rate it with a thumbs up, and I'll follow up with another video where we get into kind of setting the oscilloscope up and the more advanced features. But your oscilloscope probe is where you're going to pick up your signal. And this oscilloscope happens to have 2 channels. I'm just using 1 channel, which means we can actually view 2 signals at the same time. Your probe is what you'd connect onto the signal you're measuring, and then you have another lead, which is in essence the ground lead for the signal. So I've got these connected to a reference signal, which you can use to calibrate your probes with and what have you, but it makes a nice easy sample signal on the actual scope itself. So what I want to represent here is what we've just chatted about, is that whole matrix that you have on your display. My oscilloscope isn't a 10 by 10. As I recall, there's 8 divisions going up representing the signal level or the voltage, and then mine has far more across the time axis, I say, which I really like because it allows me, if I've got a slow signal, I've got more time to actually view the signal. And as you can see here on the display, it's showing the actual time per division along the x-axis as 500 microseconds, and we've got a square wave represented here, and you can see it says channel 1, and it's got 1 volt, and that is in essence 1 volt per division, each one of these. So that shows exactly the breakdown of the display. So let's move on to the next bit. So now let's have a look at potentially the types of signals which you can have coming in on your oscilloscope, and how potentially that they would be represented. And this, of course, there are thousands of types of signals that you can get to view, but let's have a look at a few. Now, the one I wanted to point out was something which a digital multimeter can represent very nicely, is a signal at a certain voltage level that stays the same. And on an oscilloscope, that's still a signal, but it's going to be represented by a straight line, as this red line represents here. So your level stays the same, it's not changing over time, it's just going to be a straight line. If you had to connect your oscilloscope up to, let's say, if you could connect it up to your mains electricity safely, and you're looking at the signal of the AC, you would see a sinusoidal wave appearing on your scope. So it'd be something that would be going positive and then coming down negative. Now, something else to highlight is that you have a kind of middle line on your oscilloscope, which in essence represents your kind of 0 volt line. So above would be positive, below would be negative. But that's also relative, because you can make adjustments to pull a signal into your frame of view within the display and then make measurements. So you don't necessarily have to worry about that being the negative or your 0 line, because you can count the divisions when you want to take measurements of a signal. But this would obviously represent like an alternating or a sinusoidal signal that's coming up and down. We have here in green, I've got showing a square wave pattern, which might be a digital output from some kind of device. It could be a signal from a pulse width modulated device, like a solar charge controller, which is sending a square wave pulse width modulation to actually charge something. Then over here, what I'm showing is you could, let's say we hooked this up to a capacitor that was charging over time. And as you connected the capacitor and you had a battery or a variable power supply attached, if you set your time base slow enough, or even if things were happening fast, you might see a signal like this, where the voltage is initially, or the charge voltage is initially low in your capacitor, and then it starts building up over time. And that would perhaps be the trace or the signal representation you would actually get on the screen in that case. Right, so I've just gone and disconnected the probes from the kind of test signal, and I've gone and connected them to a 9-volt battery. And if we have a closer look at the display in this case, you can see I don't have a signal on the display because I haven't pushed any auto button to go and find the signal. And the problem is that the voltage from the battery has set the level of the signal that's put it out to the display. And there's a little indication of that on my oscilloscope. You've got this little arrow which points that the signal might be sitting higher up. So this is where it leads into two things, is me showing you what that signal looks like, and then using the buttons or knobs to actually bring signals into view. So what I'm doing now, I'm using the vertical position button, which we'll discuss now, to bring that signal down so that we can have a look at it. And as I showed you on that diagram, this is what a multimeter would perfectly represent as a reading if you put it across that battery. It's a straight line because the value is not changing, so it's simply a straight trace across the screen. Now as I bring that down, what you'll see is that on here there's a volts position, and it's showing negative because in essence the 0 point is being moved down because I'm adjusting the vertical scale. So if I put it on where the 0 used to be, you can see it actually shows a reading of -7 point something volts. And that in essence is the reading of the battery. It's just over 7 volts. And there we go. I've made the adjustment to actually bring it into view. So let's have a quick closer look at some of the adjustments you can do on a oscilloscope. Right, so once we have a signal which we're inputting into our oscilloscope, we probably want to go and have a closer look at it and play around it on the screen. And the reason for doing is that you probably either want to take measurements of the signal to understand the voltage, or have a look at if there's any noise on a signal or what have you. And to be able to do that and get a closer look and play around with the signal, we have certain knobs where we can adjust the parameters of what we're seeing on the screen and that signal to make it easier to analyze. So I'll go through what adjustments, the basic adjustments that we have on an oscilloscope. So the first knob, which you actually saw me playing with there, is a vertical position knob, and that is per channel. So each channel, if you have several signals coming into your oscilloscope, each of those channels will have its own vertical position knob. And what that allows you to do is merely, without changing the scale of the signal, is to position it up or down. Because depending on what scale you've set for your oscilloscope, it might be out of range of the display. So as you saw, I had that signal from that battery. I had to pull it down so it was in range of the display and of the measurement values which were pre-selected so that I could see it. And that's that vertical position knob. Very, very simple to use. It can get confusing sometimes when you have a signal, and it certainly catches me often when a signal is out of view and you don't know whether it's at the top or the bottom, and you adjust and you adjust and you can't see it. But there I'll show you often all oscilloscopes generally have an automatic button which will automatically pull a signal into view so that you can make your adjustments from there if you're a little lost. Then you have a knob which changes your horizontal position, and again that goes for all channels, so that you can move your signal around on the horizontal or kind of time axis so that you can view a certain part of it. Your signal may not be symmetrical, it may not be a nice square wave, and you might want to see a particular part of it. Or, and we'll get down to it with the scale, you may have changed the scale of your signal and you're only seeing a small part of your signal, and you need to pull that into view. And that's what that horizontal position knob allows you to do. The next thing then is the voltage scale, and this is where it kind of gets more interesting. So this is where I mentioned you can adjust your volts per division. So each one of these squares, you turn that knob and you can adjust that scale. And in essence what that does, it's like a zoom feature. So it's allowing you a closer view of a particular part of the signal. So in essence, as an example, the sinusoidal wave, if you changed the scale at which you're viewing this, you could in essence zoom in so that only the top part of the signal was in the display, so you had a zoom view. And that is by literally changing both the voltage scale and even the time base. And that's the next knob, is your time base, and that's your seconds per division. Obviously on your x-axis you can change the amount of time that you want displayed in your screen. So do you need more time to see more of the signal, or do you want to adjust it for less time so you're seeing a smaller part of the signal in essence, or you need to adjust it to fill in, to show a whole period of the wave, a complete cycle of a wave. And that's what that allows you to do. Then another interesting and important adjustment is your trigger position. And that trigger position is something I'm going to demonstrate now. You can adjust that so that it basically gives you a stable view of your signal coming in. Your signal might not necessarily be a clean one which is being displayed in the same position of your display the whole time. And that can be rather difficult to evaluate and have a look at a signal if you want to keep it live, if it's jutting around and moving around. So what your trigger does is you then set a level at which you want your scope to capture that signal. And it's adjusted down on your kind of voltage division. You move your trigger down to kind of the middle point of your signal. And there are other variables which I'm not going into here, where you can have it edge triggered or leading edge or lagging edge triggered or what have you. But you set that trigger point so that in essence your wave is formed hopefully in a constant view. So you get a nice stable view of your wave that isn't moving around all over the place. And that's your trigger position, and that goes for all channels, and that you will see is something that you adjust on the side here to the middle of your wave. So let's have a look at those little bits and pieces. Right, so the first thing I'm going to demonstrate as we look at the signal here is if you can note, even though this is a stable wave that's coming in from the kind of the signal source on the oscilloscope, it's jumping around a little bit, but now you could have a signal really jumping around a lot more than that. So there's a trigger point which can be set to stabilize, and if you set it in the right place, it will then stabilize the wave. So over here on this oscilloscope, there's a button over here, or a knob I should say, which you turn down. As you can see on the display, there's a line which then comes down. And as I move that down so the trigger point is right in the signal, you can see how you get a nice stable waveform on the oscilloscope. Then if we look at the positioning, I can obviously move the signal down. I may want to have that signal down in the display at a middle point, because that's where I want to take some readings. And that's where this vertical position knob then helps me move it. I could move it so that it sits nicely on these divisions, so I can make measurements. You do have a facility again, and it would be something I can show you in the second or more advanced tutorial on oscilloscopes, where you've got tools to help you make measurements. But what you can do is position your signal with this in place so that you can easily count or far easily take measurements of your signal. So I could put it up on a line, and we'll put it up on that base line. And we know that we've got 1 volt per division, and if we count the divisions 1, 2, 3, we know then that our signal, the height of the signal, is in essence 3 volts. We can also see from the time scale, and we may have, this is where we end up playing with the horizontal button, is to position the wave to either get into a position which is easier for us to view on the horizontal scale to make measurements. So you can put it exactly on the divisions, and we know that our time per division is 500 microseconds. So if we wanted to understand the period, and a period is a cycle of one waveform. So from the start here, there's 1, 2 divisions before we get a complete cycle of the wave. From, let's say, a lagging edge to another lagging edge. And 2 times your 500 microseconds will be 1 millisecond. So the period of this signal is 1 millisecond. And that can be deduced from literally doing that measurement on the display there. Right, so now we may want to have a closer look at the signal. And then we can refer to, on your horizontal scale, which is your time base, we can use the knob to adjust the time base. So if you keep an eye on the time scale at the moment of 500 microseconds over here, as I turn this knob, you're going to see that's going to change. So I'm in essence decreasing the amount of time that we're showing in the screen, and then in essence zooming in on the signal. So as you see, as I adjust it, I can then get a closer look at that signal as we go in, and as I fit less into the time frame of the screen. Likewise, I can do the opposite. If I go back to where we were, 500, I can increase the amount of time that we're seeing per division or right across the screen, and then I can see more of the signal. So as you go out, it may just look like a lot of noise, but that's the beauty of obviously having an oscilloscope. You can then have a closer look at a signal and see how it's made up and what's going on your input signal. So that's your time base you can adjust, and then obviously you've got your vertical scale or your voltage scale, which you can adjust on the knob over here. And as I adjust that, I can adjust it so that I'm showing 2 volts per division. You can see that adjustment here, and in essence, as you can see, it's acting like that zoom function. So if I had a signal with a bigger voltage level, I could obviously adjust that to fit into the display that way. And again, I can take it back up so that I can see, in essence, zoom in and create and get a different view of the actual wave, and adjust for signals of different varying voltage signals, voltage levels that come into display. Right, so before we end this tutorial, I thought what I'd do is I'll quickly show you again one of the favorite things which I like using an oscilloscope for, and that's for showing a measurement over time of, let's say, something like a hybrid or supercapacitor being charged up. So I've got my variable power supply set with a voltage and a current setting, which I'm going to apply to the capacitor, and I want to see over time what that build-up is like. Now the oscilloscope is in a kind of scan mode. It's not being triggered by a high frequency signal coming in. I've got my time base set to 1 second per division. So I can show quite a few seconds. You can actually see the scan going across, how slowly it goes across, and I've got it set to 1 volt. So my reference is set at the 0 line. So as you can see, we're just under 1 volt of charge in the capacitor currently. If I go and change the time base on the scope, you can actually see if I change it up to half a second per division, how it scans faster. And if I change it like there, I've got it 2.5 seconds per division, it goes slower. So I'm now going to switch on my variable power supply, and it is slowly applying a voltage to that capacitor. And you can't see what's happening a great deal in the amount of time that I'm allowing on the screen. But if I go and, let's say, reduce that time to, let's say, 10 seconds per division, then I'll get a slow representation of what's happening on the charge into that hybrid capacitor. Now I'll time lapse this so that we're not chewing up too much time viewing it, but you'll get an idea of what you can do by just changing those, making those adjustments so you can set the parameters for your display for the signal that you're trying to view. And that's ultimately what you're doing with those adjustments. So as we can see, not much, I couldn't represent much because my volts per division was not really fine enough to see the climb in the charge rate on there. So what we're going to do, I'm going to change that scale to something that's more fine so that we can have a better representation of what's happening. Now because I've changed that scale, I need to adjust the signal vertically down so that I get it into the screen again, so that I can see what's going on. I'm going to pull it down so I get it down to the baseline. I'm going to remove the charge from the capacitor and then we'll start again. Okay, so I've removed some of that charge from the capacitor, and as you can see I've got the trace representing the current voltage level in the capacitor, and that's sitting a little bit high, so I'm going to adjust it down so that I get it to the center line, so I've got more room for movement as it charges up. And as you can see, I've adjusted the volts per division to 200 millivolts this time. So I should, in theory, I've got a far more sensitive and far more granular scale on the Y scale or the voltage scale. So I should start to see things building as I apply the charge from the variable capacitor or the variable power supply. So let's just switch that on and see what happens. And there you go. You can quite clearly see I've got a representation of what's happening as a charge is actually building up in that capacitor. And by making those adjustments on the various knobs to change the scale, it means I get a better view of what's happening over time. Let's see if I can make it more sensitive. So there we go. I've changed it now down to 100 millivolts per division. And again, it just allows you that granularity to actually see what's happening with a signal. In this case, it's obviously a very slow, low frequency signal. But having that capability of those adjustments, then you can change the parameters to suit your signal and what you want to see from your signal. So there we go. I've actually just switched off the charge from the variable power supply, and you can see it actually shows there's a nice linear progression or growth of charge in the capacitor. And as I've switched it off, you can see there's a sudden drop and then the slow discharge over there. Okay, and the last thing I thought I'd just leave you with is just to show you another feature which we can explore further in the next series on this, is capturing a signal so for analysis. So if something's happening very quickly, you may want to capture that little impulse or little signal and then analyze it. So what I've got here is I've got a capacitor of a lot smaller value. It's only 10 microfarad. I've got it hooked up to my variable power supply. So with that rather noisy signal from the power supply, I then go and set a trigger point so that I can catch a piece of that signal. What you're then able to do is, once you've actually captured that signal, is you can then go and change your time base and your volts per division so that you can go and have a closer look at that captured signal. And here it depends on the amount of buffer storage that your oscilloscope has, and there's a little graphic representation at the top as to what you can do or how much of the wave you've got, so that you can go and play with it and have a closer look at that signal. Okay, so I hope you've gained some value from that exercise. It's certainly still a learning curve for me, as I don't make much use of oscilloscopes, so I'm kind of feeling my feet along the way as well. If someone happens to notice if I've made any mistakes or errors in that, please post a comment, because then I'll either annotate those and pick up on those. As I said, if you do want to see more in this series, and the way I'll know you want further in this series is by rating the videos with a thumbs up, and then I'll jump into some of the more features and functionality of an oscilloscope, because there really are loads and it's a really useful tool. So thanks very much for watching. Do subscribe if you enjoy this series, and I'll catch you for the next one. Cheers.